What is going on, guys? My name is Hussein and welcome to the Backend Engineering Show. Today we have a question, actually a database question, and I thought I'd make a video answering that question. So that question goes as follows. Hey Hussein, I have a 2 million row table that is used in my CRUD Python app. I'm worried that as the table grows, my inserts will slow down. Should I consider sharding my database or partition that table? Thank you. So this is a common misconception where people think that the larger their table, the slower the inserts, which is absolutely wrong statement. It has some validity, but it's an incorrect statement as it is, because inserts are the fastest thing you can do. If they are vanilla inserts, you're going to the end of the table and you're inserting rows immediately. So it couldn't get any faster than that. Why? Because we know where the end of the table is. It's a big O of 1, and then slamming that block of data at the end of the table is just an IO. So it's always fast, whether you have 3 rows or you have 100 million rows or you have 3 billion rows. It does not matter. Why? Because it's a big O of 1. We know, and we insert that. Queries, on the other hand, are generally proportional with the size of the table, because you need to look up something. And that when I say queries, I mean select, I mean update, and I delete. Because when you want to select something, you have to provide some sort of a criteria to look for it. And assuming there are no indexes, you have to go through the table and then one by one check the rows. Now, indexes make things faster, but that also has a cost, right? Essentially, through going through the index to find what you want. And now, once you found it, you can perform an update operation on it. And that is, the update itself is not that bad. Well, it depends on what other structures you need to update. But the act of finding when you to update is generally slow, and the larger the table, the larger the things you have to look through, right? And you might say, hey Hussein, I have an index. Well, the index eventually gonna get large enough for you that even looking up through the index can be expensive, especially if you have so many, your values that you search for are just so repetitive and exist everywhere. So it can be painful. Deletes kind of exist in the same procedure as well. We know that inserts are fast, but now let's address the people in the comment, because some of them say, but Hussein, but yeah, so inserts can get slow when you have so many indexes on your table. So now what do? When we have a beautiful table that doesn't have any index, as I just described, we're inserting the row at the end of the table, and then that's it. You're done. You just updated the heap. But what if you have indexes? You have first name index, you have a last name index, you have age index, you have, I don't know, salary index. So now, once you inserted that, that's one operation. But those indexes need to be updated with the new values for each column, so that you can search for it in the future, right? So you have to update these 4 data structures. If you have 4 indexes, you have to update 4 indexes. So inserts affect these indexes, and this has to be happen atomically. We cannot do it asynchronously, unfortunately, right? Because if we do it asynchronously, Hussein, let's just insert the table, right, and commit the operation, and then asynchronously we're going to update the indexes. Some people thought about that, but what if a query comes in immediately after that? Well, you're searching indexes that essentially outdated, and if you don't give me the result back, I don't care what you say, your database is not consistent, and as a result you validated the C letter in the ACID. As a result, your database is not ACID, right? And you can add fancy words like eventual consistency and all that jazz, but to market your database, but yeah, it's inconsistent nevertheless, right? So now, yeah, inserts can get slow the more indexes you have to update. These are usually negligible, right? this is something we don't really pay attention too much. If you have, unless you, this is something you have to look at after you exhaust all other things. Like let's say you have an event that is captured in your database upon insert, and you go take that event and you do stuff based on an insert, like a store procedure. You execute a store procedure to query a REST call when you insert a row. If that insert is slow, it's on you, right? So make sure that your database is not doing silly stuff like that. Obviously, the inserts will be slow, but native vanilla inserts are fast in general, right? So, what else? We're going to talk about, since we're talking about indexes, right? Might as well mention the advanced stuff people doing to optimize inserts. And this is the level of the Facebook and the Google of the world. This is not you and me building to-do apps, right? Or CRUD apps. It doesn't affect us, but for the sake of them mentioning, and I talk about it in the database and my introduction to database engineering course in details. If you would like to go get that course and support the channel, it's a very it's actually a bestseller on Udemy. I was surprised. Thank you so much for all the lovely. It's 4.7. Yikes, that's really good stuff. So appreciate it. Thank you. Check it out. Over 14 hours worth of content. Good stuff. The data structure of the indexes that we need to update as a result of inserts can matter, can slow down your inserts. So for B trees and B plus trees, there is this concept of rebalancing, right? So when we insert a row, so say it's an empty table, you insert the row number 1, value number 1 of this column, you get it in the root, right? You've insert 2, you get it to the right, and you've insert 3, right? 3 is greater than 1. What happens here is, depending on how many children you have in your B plus tree, the tree is reshuffled. So the 2 becomes the parent, and the 1 is shifted to the left, and the 3 is shifted to the right? And the more rows you insert like that, this reshuffling and rebalance to keep the tree as balanced as possible, unlike binary trees, which are just literally, there is no balance to them, right? You can have a binary tree that's like that. B plus trees, because we're balancing consistently, especially if you have lots of inserts, lots of inserts, that you can start feeling, you'll feel it. Eventually you'll feel it in the insert that is slowing down because of this updating and rebalancing that needs to happen. It's not that as bad, but it is bad enough that Google has invented a new way of managing append only workloads and insert only workload to optimize that, to avoid this rebalancing of the trees, and also to avoid hurting the SSDs, because B trees, as a result, we talked about that, right? We're updating in place these structures, right? These internal nodes and the leaf nodes. We're constantly updating. Updates, SSD hates updates because there is only limited amount of shelf life to these pages on the SSDs, and if you keep doing it, right? Yeah, SSDs does all sorts of this this balancing the pages, removing and taking things from different page and writing into another page. This constant thrashing on your SSD is gonna hurt it, and as a result, you reduce the value of the SSD. So Google invented this idea of log structured essentially indexes, where how can I make my indexes so that I don't need to update them if I'm inserting new stuff? Why am I performing an actual update? I want this to be a nice. I don't want to go locate location and then change it in place. I don't want to do that. I want my always everything an insert. I always keep insert. So they invented the idea of log structured merge tree. So everything you write it sequentially nicely in memory as level 0. They call this level DB. This is what's called. The levels are getting everything in memory. And you might say, Hussein, if we're writing in memory, isn't this not durable. No, we also write it to a write ahead log into disk, but also sequentially written so that we don't lose it in case our machine just decided to shut down, right? So we keep it. So this is the first thing. And as we don't sort or do anything, right? So, but as this level 0 gets filled up, what we're gonna do is asynchronously, we're gonna merge, take this, sort it, and write it to a level 1 on disk structure. It has to be sorted. And we go, and as level 1 gets filled up, we do the same thing. We take that, resort it, and then write it to a new location. Always write new. It's immutable. That means we don't change it in place. It's always take everything, insert, we append it in the middle. Obviously, this created all sorts of new problem, and they are trying to solve it because now queries become slower if you think about it, right? Because you have to query level 0, and you have to query level 1, and you have to query level 3. If you're lucky, if the things that you just changed, obviously they're gonna become in level 0, right? Then you're gonna find it in the first level. But again, they add all sorts of Bloom filters and things to make things faster, but this is not our topic. But yeah, just answering the question, you can see how complex a CRUD app is, right? It's not as simple as you think it might be. All right, so most of the time you don't have to worry about LSM versus B3. B3 is enough. If you start feeling it in the billions of rows, then you might worry about it, right? But LSM trees are getting popular. Cassandra uses LSM trees. RocksDB uses LSM trees. I believe MariaDB has an LSM tree indexes. But that's it. All right. So let's talk about select, update, and delete, which is the RUD or part of this, or read, update, and delete, right? CRUD. So when you select, update, and delete, we're not worried much about the deletion and the updation of stuff. Updation, is that even a word? Updating of the things. We're worried about the finding of the stuff that we need to update. If you're finding a lot of stuff, that is obviously going to take you more time than finding fewer set, right? That's why you don't see public APIs allowing you to update, to do a set updates. Instagram, they don't let you mass follow or mass unfollow because they know they can't do it efficiently. It's very, very hard to do efficiently. Find me an API on one of these applications that you log that has a mass approach where you just, hey, I want to do all of this. I want to delete all these emails. Gmail just introduced this feature, but they do it very efficiently, asynchronously on the backend as a job, right? And even though, like, how do you do it, right? Just like you submit all these, we almost never do it right, this mass update or mass deletes. That's why keep your API simple, even if that's as a cost to the user experience. Yeah, if I want to delete it one by one, sure, but don't let the user select like 100 million and then delete that. That just will kill your performance, obviously. So now, selecting stuff is what you need to pay attention. If you solve selects, you get update and delete for free, okay? Plus the cost of the B3 updating and all LSM updation of the indexes, right? So now you need to figure out what indexes you need to create, not to be a lot of indexes, just enough for you to perform these selects, update, and delete. Don't add indexes just for the sake of indexes, like for a to-do app or CRUD. Yeah, what are you reading exactly? You're displaying the list of to-dos, right? So think about what you want to show and what kind of queries and what kind of filters are we executing. If I want to delete one to-do, like, hey, I marked it as done, that's an update technically, right? If I want to update it, how do I search for it? So use primary keys when possible. Do not use GUIDs as primary keys. We talked about that in MySQL specifically. That's just a bad idea because of clustering by default. Postgres, you might get away with it, but essentially the randomness of GUIDs just kills the performance. Database don't like random things. It likes sequential write, so it can cache and it can predict the page where the next row is coming. form, right? If you're inserting value 1, 2, 3, 4, 5, they all nicely tucked into one page, right? So the next value 7, you're looking at it or writing through it, it's gonna most probably be in the same page, right? But if you're inserting values, I don't know, 7 and then 100,000, and then the next file is 9,000, and then the next one is 200 million. These are located in different places in disk, and as a result, these random seeks across all different places, IOs, can hurt your performance essentially, right? So sequentially, always beautiful, always better, right? At the end of the day, now see, right? I've been talking for how long now? I didn't even mention partitioning or sharding. That's our problem here. What scares me really in the current premature optimization world is all this talk about, hey, let's do microservices from day one. Hey, let's do sharding from day one. You don't need to. Avoid it. Keep things simple. Simplicity always wins. If you need, don't do premature optimization. Don't try to complicate your structure just because you might need it in the future. Sometimes you have to be optimistic a little bit. It's like, okay, well, I really need it. If I need it, I can add it in the future. If you can answer that question, then don't add it, right? Again, that's just my opinion. You might have a different one. I would love to hear it in the comment section below, essentially. But I talked about partitioning. I talked about sharding in my course. I talk about these two concepts a lot. I prefer partitioning over sharding. If you can partition. Avoid sharding unless the final solution. Obviously, there are tools now that allows you to do that. But my argument is, yeah, there's a tool that allows you to do that, which you don't have to you don't have to do it yourself, but you have to still manage this thing. Like Vitess is a good example, right? Vitess allow you to do sharding from day one, but you just added an extra piece of infrastructure that you have to manage, not anyone else, right? Unless you're paid for, everyone is going to support this for you and they do it for you, then it's a different question. But if you don't need it, don't do it. Partitioning can be implemented later even if you have one monolithic big large table. Eventually, if you want to do sharding, the beauty of sharding partitioning is you get smaller tables in the same machine, right? Forget about, you don't have to avoid it in this I'm talking everything here is in the same machine essentially, right? And yeah, if this machine eventually can't scale up, you can always do replication, replicate your reads into another server, so you can do that stuff. But even though, just push it to the limit, push that vertically scalable thing to the limit before you introduce replication, before you introduce partitioning, right? See where you can, because so you can squeeze so much performance from the existing fundamentals that we know, right? Don't just add things because, hey, let's make it faster, let's do sharding. Nah. Because what do you do with sharding? You just make your table smaller. Well, you can do that with partitioning, right? Or you can make indexing. You can do partial indexing, for example, to create indexes that are efficient, that only for the things that you actually search for. Even better, only add indexes for the things you actually search for. Don't add indexes for things that you're barely searching for. Or just because one app like admin is using it, you're adding an index and killing the performance for other stuff. Probably not a good idea. All right, guys, I think I'm gonna stop right here, but hope that answered the question. I guess should I shard or partition the application? The answer is it depends, but no. Don't shard unless you absolutely need it. That's my answer. Not my answer. Obviously, might not suit you, but essentially, my motto is always keep things simple. Only introduce things when you need it. Only solve problems that you have. Let's say, okay. Don't solve problems that you don't have. That's a nature in us engineers. We always want to solve every single problem or every possible problem that we don't have. We would think about a problem and we introduce it to ourselves, What if this happened? What if a camel passed the road? What should I do? Oh, what if a meteor hit my house? My house should have a high availability zone. Like if I disrupt my house, I should have another house backup. Sheesh, man, if a meteor hit the earth, we're done, right? Sometimes don't over ask this what if. It's just, I think it's a slippery slope. Again, everything here is my opinion. I'll pass the question back to you. What do you think? I'm going to see you on the next one, guys. You guys stay awesome. Goodbye.